So thanks, Chris. Thanks, everybody. So I'll talk about this work that Chris mentioned about chasing convex bodies. It's a question that had been open for some time. And the answer turns out to be very clean. And I particularly sort of enjoy explaining it. So I'm hoping that I'll be able to give you most of the ingredients of the proof, if not all. So let me first define the problem. Oh, I should mention it's with my students, Ziye, Ziye Tang, and Guruganesh. Okay, so let's see the question. So the question is easy to state. The algorithm, it's an online problem. So the algorithm sees the sequence of requests. What are requests? The requests are convex sets. And the algorithm controls a point. So every time you see a convex set, you have to move your point into the convex set. And all this is happening in d dimensions. What do you pay? You pay the distance that you move. So you see another convex set, you move, you see another, you move, you see another, you move. And your cost is racking up. This is the movement cost. Now what you could do is you could look back in hindsight after having seen a sequence of these convex sets, and you can say, if I know this entire sequence, what would be the best way of handling this sequence of requests? So I still have to hit K1 before K2, before K3, before K4, and so on and so forth. But I could be smarter about where I move since I know the future now, so to speak. And that gives you the optimum cost. And as is traditional in online algorithms, at least in competitive analysis, we look at the competitive ratio, which is the cost of the algorithm over the cost of the optimum on the same sequence. And then we look at the worst case sequence, the max over all signals. So this is the problem that we want to consider. It's called convex body chasing. This was defined by Friedman and Lineal in '93. And I'll come into some details about this question. One thing, by the way, you'll notice is that this question can be cast as a convex program. You're trying to minimize this convex function, which is the sum of norms, where each of these xt's lies in some kt. And assuming that there's a reasonable representation of the kt's and stuff like that, it's just a convex optimization problem. But now the issue is that the KTs are arriving online. So this is the real challenge out here, how to deal with uncertainty about the future. Maybe I should mention one special case and one extension. The special case is when the convex bodies are nested. So each time I give you a body, which is a subset of the previous body. Okay, a simpler case. And in this case, actually figuring out the optimum is particularly simple because all you have to do is you have to take your original point and project it onto the final body of the sequence. Okay, so the nested case seems like a substantially simpler case. And by the end of the talk, we'll see that actually it's not substantially simpler. In fact, it's once you solve the nested case in the right way, then the solution for the general case also follows. And that's the kind of takeaway that I want to mention. An extension of this problem is the convex function chasing problem, where instead of at each time, I'll give you a convex function instead of a convex set. And so what you now do is you now have to give a point xt. And what you pay is you pay the function value at that point plus the movement cost as before. So if the functions were just 0 and infinity, in some sense, the indicator functions of these convex sets, then you get back the convex body chasing problem. But this is more general. Okay. And again, it's a convex optimization problem and same kind of issues. So one thing, and maybe I should mention right off the bat, is you might think, oh, the convex function chasing problem is much more difficult. But it turns out that the convex function chasing problem is of almost the same complexity as the convex body chasing problem, but in one higher dimension. So let me give you a sense of how I'll do it. If you gave me this convex function, so let's imagine that my convex functions are just one dimensional. So if you gave me this convex function, I'll ask you to chase the epigraph, this convex body. So maybe you'll move to a point, you'll move to a point somewhere in this gray region. Then in the next step, I'll ask you to give me a point on this one-dimensional, or on the one-dimensional lower subspace. Then I'll ask you to chase the epigraph of the next convex function, and so on and so forth. So each time you have to give me a point out here, give me a point down there, give me a point out here. And in some sense, the vertical distance is capturing the function value, and the horizontal distance is capturing the movement. If you didn't get all the details, it's not important. If you sit down for 2 minutes, you'll be able to see it. So the convex function chasing, which seems, which comes up in several applications, is actually, just the same as convex body chasing, if you don't worry about this +1 in the dimension. Okay, good. So maybe a quick word about why we are interested in these problems. It's basically a very general framework, captures a lot of online problems. Online algorithms have been studied for many years now. And this is a very general object. Like, for instance, if you wanted to capture the paging problem, you'd be chasing a fractional algorithm for the paging problem. You'd be chasing convex sets of this form. Okay, I'll just very quickly go over this. This is somehow saying there are n pages, and x sub I is going to capture how much of the ith page you have in memory. It's a fractional version, remember. You want to make sure that you have exactly k pages in your cache, and that at each time t, the requested page is fully in your cache. A simple idea. And similarly, you can capture many different problems. One thing you'll notice is that in these cases, you might have non-Euclidean norms. So the problem is interesting for other norms as well. And actually, I didn't mention, whenever I write norms, in this talk, I'll assume Euclidean norms, but in general, you might be interested in other norms. So it's a powerful generalization, much like the metrical task system problem, if you've heard of that before. And the question really was, can we get a unified and perhaps simple algorithm for these problems? And so people also approached this problem because this was similar to this idea of online convex optimization, which has been widely studied. There are some salient differences. In our problem, the decision maker sees the function before playing the point, but now there is a cost for changing decisions, and we are studying the competitive ratio, not the regret. So there are important differences, but the two are kind of in a similar league, I would say. And people have studied this quite a while, and to model various kinds of online optimization problems. Maybe I won't go into details out here. I would like to give some technical details rather than this. Okay. So that's kind of the background. Here's the problem, and here's some motivation for why we're interested. Let me very quickly give you a lower bound. So this problem was defined in this paper of Friedman and Lineal, and they showed a square root d lower bound. In this sort of snippet, n and d are conflated, the square root of the dimension lower bound. And let me tell you the lower bound. And I'll tell you the two-dimensional lower bound. So initially, I'll tell you that, look, I'm going to give you a nested instance. And finally, I'm going to make you go to one of the four corners of this square. Of course, you don't know which one. So first I say, okay, I will make you go to some point on this facet. Since you don't know where you should be and you started at the center, the only reasonable thing is to go to the center of this facet. And then I'll show you which of the corners of this facet you should be at. And so you'll take the Manhattan route, whereas you should have taken the Euclidean route. And you can see that if I had a d-dimensional hypercube, I'd make you pay square root d more than what you should have. So there's a lower bound, even in the nested case. And the question that they asked was, can we actually get an algorithm whose competitiveness is just a function of d, which does not depend on the length of the input sequence? So this is the conjecture that we're interested in. And so in this talk, I'll give you an idea of the resolution of this conjecture. And the algorithms are very clean and simple, and they'll show actually linear competitiveness. There is this gap between d and square root d for the Euclidean case. There is a lower bound of d for L infinity chasing. So if you change the norms, then d is the best you can do. But for the Euclidean case, there's still this interesting gap. It might be worth looking at it. And my sort of interest is piqued by the connections to convex geometry out here. So very quickly, a historical thing, 93, Friedman and Lineal defined it. For a long time, not much really happened. And then in the past decade, people started looking at restricted cases of it. And then there were these algorithms which solved the nested case. Somehow the focus on the nested case was crucial. Once we got the idea that the nested case is important, then we were stuck a little bit, but once you'll see in a moment. So then we could solve the general cases. And there's a bunch of people who are working on this. And in some sense, I want to give you a sense of this whole line of work. Okay. So the rest of the talk, and in the rest of the talk, I have exactly 10 minutes if I don't want any questions, but we'll see. I'll recast this problem as a bounded version, and I'll give you some strawman algorithms, and then maybe give you an idea of the nested and general cases. Okay, good. 1, think of the following problem. Don't worry about the general problem. Think of the following problem. I'm going to give you convex sets where the first convex set is the ball of radius r. And then every other convex set is sitting inside this ball. I'll promise to you that the optimum pays about r. And I want to pay at most some function of d times r. And basically, my claim is if you can do this, then using some guess and double ideas, you can solve the general problem. Okay. So this is the problem, R-bounded instances. Let's try a couple of algorithms just to get some intuition. So the first algorithm is greedy. Just move to the closest point in KT. And this is kind of a bad algorithm. And here's an example. It's basically, I'll give you these convex sets which are shifting in this way, and I'll make you go in spirals. Well, what you should do is you should just move to the center. Duh. Okay. So the greedy algorithm, greedy not so good. Well, we kind of knew that. Okay. Here's a sort of more interesting one. How about for the nested case? How about I move to the centroid of the algorithm, of the current body? Now notice that if you move to the centroid of the current body, you can use Grunbaum's theorem to say that, look, half of the volume must have been cut off every time I have to move. So the algorithm, let me just be precise. If I am already in the requested body, I don't move. If I'm outside the requested body, I move to the centroid of the requested body. Okay. And Grunbaum's theorem is very nice out here. Every time the volume shrinks, by a factor of about half. So this is great. You move and the volume starts shrinking. But you're not interested in the volume, you're interested in the distance. So here's an example. So I started with the box. I gave you this slanted trapezoid. You moved pretty much a constant fraction of the width of the body. And then I'll flatten out the box again. And then I'll give you a slanted thing. I'll flatten out the box again, and I keep going. You keep shuttling back and forth. Bad idea. Good. So here's one idea, and I'll just very quickly, it's an impressionistic view of what's happening. What will happen after a little while? Suppose you kept moving back and forth. You kept paying, the radius of the ball r, you kept moving back and forth. After a little while, one of the directions will become flat. It'll become very thin. It'll become like a tortilla, a pancake. And then what you should do is you should just ignore that thin direction. Because the body is so thin, how much can you move in the thin directions? So the main idea is you kind of project out thin directions. you only look at the centroid along the fat directions. And this we call the recursive centroid algorithm. And more or less, after order log D steps, the directions, at least one direction will become thin. Thin means, 1 over poly log of the radius. Okay. And then there are D directions, so D log D. So this will give you a D log D. And this was a D log D competitive algorithm. And using this, Sebastian Bubeck, Yintat Lee, Yuanji Lee, and Mark Selker gave an algorithm which was true to the D competitive. But it's complicated. So let me give you a simpler algorithm. I have 5 minutes. Let me just use that 5 minutes. Okay. So I need one object I'll have to define. And this is the object you should take away from this talk. It's called the Steiner point. I did not know about this before this work. It's a beautiful object. The Steiner point is the average of the extreme points in all directions. So take any convex body and look at the average of the extreme points in all directions. That's the Steiner point. I find this picture very useful because if the body is a polytope, look at all the extreme points. These are the vertices of this polytope, and look at the normal cones and look at the size of the normal cones, the measure of the normal cones out there, and take the extreme points, the vertices, weighted by the size of the normal cones. This is the Steiner point. And here is a new algorithm for the nested case. Move to the Steiner point. Okay. So I'm not going to give you the proof. It's decompetitive, no logs, no nothing. And I'll just give you the intuition for this bad example. So what's happening? So let's look at the Steiner point of this object. So you'll move to the right, and then you'll come back. But the next time, what's happening? So if you look at the previous normal cones, they were fairly imbalanced. But if you look at the slimmer body, now the normal cone started getting balanced. So you don't move as much. It's kind of a self-adjusting. I think really of this as a smoother version of recursive centroid. It's taking care of the fat directions and the thin directions in some organic sort of way. A beautiful object. Okay. So it's a decompetitive algorithm. I don't have time for a proof. If I had 5 more minutes, I would give you the proof. So I'll just flash the proof out here. It's 1 page, 1 slide, not even 1 page. But anyways, whatever. Here's an algorithm. So the algorithm for the nested case was moved to the Steiner point. Okay. So let me give you the algorithm for the non-nested case now. Basically, the idea is if you have the right algorithm for the special case, it should generalize. And this is the right algorithm. So let me tell you the thing. Let me ignore all this. Okay. So here's what I'm going to do. I'm going to define a bunch of nested sets, and I'm going to run this nested algorithm. So what's the nested set? I don't know where opt is. So I'll define omega t to be all the places where opt might be at time t, having served all the previous requests and paid at most r. Okay. So in this case, opt can be anywhere in this gray region because it has to be inside K1, and then it can go anywhere for a total distance of r. Okay. This is my uncertainty set. Okay. Fact 1. Uncertainty sets are convex. Well, if opt could be at point X and opt could be at point Y, then opt can be at any of these, the average of these points, just by convexity. These are nested because my uncertainty gets lower and lower. Opt can move only a distance of r. So it's spinning itself down. Okay. So my algorithm is chase these nested convex sets. You'll complain. Look, I don't want to chase omega t, I want to chase kt. But I'll say, aha, the Steiner point of omega t is guaranteed to be inside kt. And here's the proof. So remember, what are the objects? Kt is the body in which I want to be. Imagine it's a half plane. this is general enough. Okay. Omega t is where opt might be, having paid at most r. Okay. So look at a point where opt might be, that is outside kt, this left point. How did opt get there? So my claim is that its mirror image according to, with respect to kt is going to be also inside omega t. So this point is inside omega t. I'm claiming this point is also inside omega t. Why? Well, this point was inside omega t because opt could get there paying at most r, right? But then opt can, instead of taking the reflection, it can go straight through and get to this point as well. Okay. So whatever is outside, what part of omega t is outside kt, the reflection of that is inside kt. Oh, and also inside omega t. So omega t looks like this. There's a bunch of stuff outside, the same stuff inside, plus other junk. And I'm looking at the Steiner point of this object. Any self-respecting notion of center, if there is more stuff on the inside, the center should be inside. Of course, this requires a proof, and there is a proof. But this is the main idea. Okay. Anyways, I'll stop here. You can talk about functional Steiner points, and there's a very nice idea of Mark Selke's that doesn't require this guess and double idea. There's some extensions. I'm not going to go into that. Let me just end with some open questions. There's, of course, the obvious open questions. Close the gaps. What if the functions are supposed to be well-conditioned functions or some other nice functions? Maybe they satisfy the PL condition or some other, some nice conditions. Okay. Another question that comes up is, this is such a general thing. What if I told you my convex bodies are nice? Can you give better algorithms? Can you give algorithms that automatically adapt to the niceness of the instance? What if there are more than one server? What if you control 2 points? There are some lower bounds, but maybe there are some nice upper bounds as well. And of course, what deeper connections are there to online learning and maybe also to convex geometry. So with that, I'll stop here.